So Monday, 15:40 to 17:30. Is it okay with everyone? Okay, so Wednesday, these hours don't suit your friend. So does anybody want the Wednesday hour to be shifted?
I would like that, but if Wednesday becomes the alternating
Yeah.
peak hours, then it should be fine.
Okay. So in any case, we will have the Monday lecture every week, Wednesday lecture every other week, and well, if you still insist that we should find some other day, we can just send you a poll asking you your suitable slots so that we can shift it. Now, in any case, we should probably send this poll. So if we can find a more suitable time that will fit to everyone, then we can also shift the Wednesday hour. But for the time being, Wednesday at 13:40 and to 17:30. Yeah, sure.
Biraz uzun oldu hocam sanki.
Okay. And before I forget, next week I will not be here, so next week we will not have any lecture. But in the following weeks, we will have the Wednesday lecture to make up for the lectures we will miss. And I suppose you have already checked the syllabus. Well, the grades, I'm kind of trying to have 2 midterms, 1 final. The dates we can talk in a couple of weeks, and we will try to have around 10 assignments per semester. And well, during the exam week, we won't have any assignments. And do you have any questions about the conduct of this lecture? Not the content, but the conduct.
I'm not added to the class, so I can't ask anything.
Yeah, okay. So are you all registered, planning to register?
I'm not registered because of my master's.
Okay. So what?
So do I. So do I.
Okay, so if you intend to follow this lecture, I don't object to visitors, but I will require you to do all the assignments and take the exams also.
Assignments meaning homework?
Yes. And just send me emails so I can add you to OptiClass so you can follow the assignments will be distributed from OptiClass. And our assistant is Emre.
Hi.
He is in 409 if you have any questions.
I'm not on 409. It's Joseph now. 409.
No, okay, so
426.
426, okay, sorry.
Can we have recitations while we're still there?
Well, the recitations are, you see, these additional 2 hours every other week. That's some of you had already also asked. If you struggle with the lectures and if you ask reviews, that is what we will be using those 2 hours. If need be, we can do even more recitations or review lectures. Now, the problem with the recitations is usually, I don't know, during the class, around 10 students show interest in the recitation and only 1 of them shows up.
It's fine by me. It's fine by me, actually. So we have the 4th hour. Like, on weeks, so we have just 1 hour Wednesday. If we can do recitation that hour. So every other week.
Well, if there is just 1 student, you can just go to his office and ask your questions.
But there'll be more than 1, I see.
I'm not so optimistic. I hope there will be more than 1. We can try next week.
Okay.
You can just review thermodynamics. That's what we will do this week.
Okay.
And the office hours, well, I don't fix an office hour, mainly because I cannot just keep them. I mean, in the last minute, there's some meeting and I'm not there. So rather than that, you can always send me emails. We can discuss through email. If need be, you can just drop by my office and we can discuss in my office. Just write to me. And I record my lectures, if I don't forget. I record them, all of them, and they will be also available in OptiClass. I will upload them to YouTube if you don't object. Well, there's always the issue with the Private Information Act, let's say. So if you ask questions, I mean, it doesn't get recorded, but it's audible slightly. So just to let you know, they will be recorded and uploaded in YouTube. Okay, so let's start with what we will be doing in this course. Well, this is statistical mechanics. How many of you had not taken statistical thermodynamics 430? You have not taken? You have not taken. But I suppose you have already taken some statistical or thermodynamic course in your undergraduate.
10 years ago.
Okay. Well, the situation is not so different for our graduates also. It has been at least 2 years or 3 years since they have taken. Okay, statistical mechanics. Well, it is closely related with thermodynamics. You see, the problem that we are trying to address here is, for example, you have taken your classical mechanics course, or even in mechanics, in the freshman mechanics. So given a potential that a particle is subject to, you can find its position as a function of time and the velocity as a function of time if we are doing classical physics. So this is not a big deal. This is just one particle. If you have two particles, if the potential is, just depends on their relative separation. Well, this problem is basically equivalent to a one particle problem. So if you have two particles interacting by a potential which depends only on their separation, this you can just separate the center of mass motion. It will be independent from their relative motion. So each one you can treat as a single particle problem, and hence you can solve it. You can find general solutions, whatever the potential is. Now, three-particle problem, or three-body problem. How many of you have read the book? So basically there's no solution, no general solution.
The book, the fictional one?
Yeah. I mean, the basic premise is still the same. There's a three-body solar system, and it's chaotic, so they don't know what will happen the next day. So that's where it starts. But the thing is, there's no general solution to it. In fact, in most cases, the system is quite chaotic, meaning that, well, you see, if you cannot solve a differential equation, usually you can just go to a computer and try to find numerical solutions for finite times. But in chaotic systems, you cannot just extrapolate that time. Even a very small change, and inevitably in numerical simulations, you have small errors. Even a small change in a short time will create a large differences in your predictions. So a three-body problem is practically, we don't have a solution. Well, let's come to any object. Typically, this has 10 to the power 23 particles. Well, I mean, you don't go out and try to solve this problem even numerically. Just asking the question, what is the position and the velocity? If you treat it as a classical system, what is the position and velocity of each one of those particles? 1 second from now, that's kind of hopeless.
Stupid question. How do you know it's 10 to the 23? Where does Avogadro's constant come from? Because no one's counted 10 to the 23 particles or anything. So
We measure the mass of atoms. We can measure them.
okay.
And so what? Let's say mass of one hydrogen atom. So that we can measure. 1 gram divided by mass of one hydrogen atom. This is the Avogadro's number. Yeah, basically it's the carbon, but the idea is the same. You can measure the mass of a carbon atom. 12 grams divided by the mass of one carbon atom. That gives you the Avogadro's number.
So it's a 20th century thing? Isn't Avogadro's number quite old? Like,
18th and 19th century.
so they could do this then?
Yeah. And Also from the ideal gas law, you can derive it. You see, on one hand, we have this one. You know, the Boltzmann constant. On the other hand, we have this one. The relation between K and R is the Avogadro's number. So we know the Avogadro's number. Well, let's just make an exercise. Let's say 10 to the power 23 particles. And let's say that we would like to solve the classical problem for 10 to the power 23 particles. How many initial conditions do we need?
2 times 10 to the power 23.
6 times 10 to the power 23.
Why? Position and velocity.
Components.
3 components each.
Okay.
3 components each.
Okay.
Initial conditions. Let's say each one of these initial conditions is stored in 1 byte. Well, this is 6 times 10 to the power 17 megabytes. 6 times 10 to the power 11 terabytes. What is the largest hard disk we have at the moment? Do you follow?
About 100 terabytes. 100
Hmm?
terabytes is coming out soon. So
Yeah, around 100 terabytes, let's say. So we will basically need 10 to the power 9 of them. This is just to store the initial conditions. Now, if you ask the question, well, can we solve this numerically? Basically hopeless. So we have to change the question we ask. Do we really need the position and the velocity of all the particles making up this, my key holder? So what would you like to know about this? In general, in your everyday life.
That's a rigid
Hmm?
body. That's a rigid body.
Okay, that's a rigid body, fine. So what would you like to know? I mean, when I am holding it, I want to be sure that it won't burn my hand. That is one thing I would like to know. Right, so I want to know the temperature. What else do I want to know?
Size.
The size, the volume, will it fit in my hand? I mean, if it won't fit in my hand, well, it's easy to know, but that's something I would like to know.
Mass or density.
The mass, or let's say the number of particles in it. So will I be able to lift it? What else would you like to know about it? The shape, well, fine. The volume kind of contains it, let's say, but yeah, you're right, the shape. Will it? Hmm? Will it stay together? Well, most of the time we will assume the shape, we will assume that it will stay together. But, I mean, on one hand we have 10 to the power 23 parameters. If we want to describe all the position and the velocity of each one of the particles making this key holder. On the other hand, what I would like to know is just a handful of parameters. Well, if you want, you would like to include the pressure. Well, can I squeeze it, or will it explode in my hand, or if I puncture it, will it explode? I would like to know the pressure,
Electrical properties.
the energy, electrical properties, magnetic susceptibility, electric permittivity, magnetization, etc. But at the end of the day, even if you think for hours, you will probably come up with at most 10, 15 parameters that you would like to know, not much more than that. We don't want 10 to the power 23 positions and coordinates. They are kind of useless for me. What I want is just a handful of parameters. How are they related to each other, how I can calculate them, etc. Now, this is where thermodynamics and statistical mechanics comes into the game. Now, one problem is, how are they related to each other? How is the pressure related to the other parameters? Or how does a change in one, if I change the temperature, let's say, how does it affect the change in the other properties? If I change one, how does the other ones change? So that is one thing I would like to be interested in. So that is what the thermodynamics does. You see, thermodynamics relates macroscopic properties to each other. There are all kinds of relations between various derivatives, how derivatives of one quantity is related to the derivative of the other one, and that is basically what the thermodynamics for us studies. How is the change in one related to the change in the other one? Now, the nice thing about thermodynamics is since it only relates to macroscopic properties, it doesn't care about the microscopic structure. So if you come up with a thermodynamic relationship between these macroscopic properties, it will be valid for the atmosphere here, for my key change, for a sun, for anything you can think of. The relations that thermodynamics gives us is correct for all the systems, independent of their microscopic property. But it is, again, of course, limited. It doesn't tell us, thermodynamics doesn't tell us how those properties emerge, how those, it relates the changes in one macroscopic property to the other one, but it doesn't tell us how they emerge from the microscopic picture. For example, for the ideal gas, this is a system that we will study frequently. We know that this is PV is equal to NKT, and just knowing this relationship, thermodynamics tells us that energy is a function of temperature only. It doesn't depend on the volume. You can explicitly prove that energy doesn't depend on volume, just starting from PV is equal to NKT. Because thermodynamics relates the change in the energy as a function of volume to what is called the equation of state. We will do this. Now, of course, where does PV is equal to NKT come from? Thermodynamics doesn't tell me that. It's initially discovered by just experimental measurements told us that gases under certain conditions, their pressure, volume, the number, and the temperature are related by such a relationship. Just an experimental observation. Thermodynamics didn't tell me this relation. But statistical mechanics allows me to derive this relation from the microscopic properties of my system. So that is kind of the advantage of statistical mechanics. Given a system, it allowed me how to drive the relation between the pressure, volume, the equation of state. It allowed me to drive the energy, the magnetization, and how magnetization changes with temperature, etc. Of course, the disadvantage is if you want to study a given system using statistical mechanics allows you to study particular systems, specific systems. So given this system, the relations I will obtain will be valid for that system. Thermodynamics, if I drive a thermodynamic relationship, it will be valid for any system, but it won't be able to, let's say, distinguish specific properties of the systems. But statistical mechanics allows me to relate these macroscopic properties to the microscopic description of my system. So given the Hamiltonian, in principle, statistical mechanics allows me to derive all the properties of, all the macroscopic properties of the system without solving the equations of motion, which is practically impossible. Now, this week, what I would like to do is just do a fast review of thermodynamics. So any questions up to here? So that at least when we actually study statistical mechanics, you will have an idea of what we are aiming at, what we are trying to calculate. So let me first make some definition, the microstate and the macrostate. Again, let's go back to my key holder. My key holder today just looks exactly like what it looked like yesterday. It didn't change, it doesn't change. So its mass is the same, almost the same. Temperature is almost the same. Volume is almost the same as long as I remove as long as I don't remove any keys, it will stay the same. So these things like the mass, the volume, that is what we call the macro state. Temperature, pressure, etc. The microstate is actually what we had been discussing at the beginning, the position and the velocity of all the particles. Or the wave function of my system. That is the microstate of my system. Now, one important property will be, we will study it in more detail, is for a given macrostate, like pressure, temperature, number. Let me just take these three as my variables. For one macrostate, now we will see there are basically infinitely many, an enormous number of microstates. In fact, statistical mechanics will allow me to go from the microstate to the macrostate. Thermodynamics only deals with the macrostate of my system. Now, any questions about this microstate, macrostate? Now, another concept that we will be using frequently is equilibrium. We will also talk about thermal equilibrium, or mechanical equilibrium, practically you can define more equilibriums, but these two will be what we will be talking over most of the time. Well, equilibrium is not necessarily steady state. Okay, equilibrium and steady state, they are two different things. As an example of a steady state, for example, let me just, a heat reservoir, a huge object at some temperature T1, another huge object at a temperature T2, and let's say that they are connected somehow so that energy can flow from one to the other one. Well, since both of these so-called heat reservoirs since both of them are huge, as time goes on, well, nothing will change. Well, this is a system in steady state. Well, the temperatures will not change, even though they are losing energy, since they are assumed to be infinitely large. Well, they have infinite energy. Even if they lose some, they still have infinite energy. Of course, this is an ideal system, but this is a steady state. This is not an equilibrium system. Although the system doesn't change in time, it's not an equilibrium system. It's not in equilibrium in the sense that we will be describing here. Well, one way of seeing it is we never have infinitely large reservoirs. So if you do this for a realistic system, the temperature of both of those systems will change in time, and hence it's not in equilibrium. But just keep this in mind. So equilibrium we will still define as a system is said to be in equilibrium if none of its subsystem changes in time. So that will still be the definition we will use, but just keep in mind that this definition can also be applicable to steady state systems that are not in equilibrium. But for the time being, a system is in equilibrium if none of its subsystems change in time. As temperature will remain the same, for example. And in fact, we will be able to define a concept of a temperature. That is why we need the equilibrium.
Sorry, can you give another example of steady state but not equilibrium? I don't understand.
Well, the example I can come up with will be basically the same as here, a waterfall.
Okay.
It doesn't change in time.
Okay.
But that is because it has two huge reservoirs, water reservoirs. It's not in equilibrium, but still.
Can we also define a steady state?
Hmm?
Can we also define a steady
Well, the
state?
reason why I mentioned the steady state is for the steady state I will also give this definition.
So
well-
how will we distinguish?
Well, once we define the temperature, a system in equilibrium has a definite temperature. One temperature and one pressure.
But somehow, if I stop the flow from one plate to the other one, it will be in equilibrium, right? There will be no flow, so it won't be a steady state, it will be in equilibrium.
For example, this system, an object at temperature T1, another object at temperature T2. Each one of these is in equilibrium.
Right.
This system is still defined not to be in equilibrium. Because as we will see in a moment, we will be assuming that all parts of the system are interacting with each other. So we will always talk about, if you want to reach what equilibrium, there should be some interaction, some flow in the system. So here, this system doesn't change in time because no interaction is allowed between two subsystems. Maybe that would be, well, I never saw such a definition, to be honest, but maybe that would be a nice criteria to add. So the system we will be looking at, all parts are somehow interacting directly or indirectly with each other, and the system shouldn't change in time. So in this case, we can, of course, study each one of them separately. Each one of them will still be in equilibrium, but the system as a whole, we will say that it's not in equilibrium.
Do we have a quantitative measurement way of how much it is not in equilibrium or steady state? And are we going to deal with it?
You see, this is also an important quantity, the so-called the relaxation time. Can you give me an example of a system that's in equilibrium in real life? Is the atmosphere here in equilibrium?
I wouldn't call it. Maybe a C.
Hmm?
Maybe a C. Maybe a C.
See? Well, let's stick with this atmosphere. It's something that's already here. Come on, don't be afraid to say yes or no.
Okay.
No.
Hmm?
No.
Well, yes and no. Yes, because if I measure this atmosphere for a couple of minutes, I will see that it doesn't change in time. The temperature doesn't change. It's in equilibrium with outside, it's in equilibrium within itself. But if I would measure the properties of the atmosphere in this room for a day, I will see that it's not in equilibrium because during a day it is changing. So even if you come up with a very clear definition of equilibrium, it still depends on what you are actually studying. Or sometimes we will talk, for example, do you remember what's an adiabatic process?
Yes.
Hmm?
No energy exchange.
No energy exchange. So is it a fast process or a small process? Slow process? Slow or fast?
Very slow.
Hmm?
Slow. It's very slow.
Well, you see, if the process is slow, then no process is adiabatic because eventually it will be exchanging energy with the environment. But we know that adiabatic approximation is a good approximation.
Right.
That means it's fast. So that energy exchange doesn't happen. You see, energy exchange, if you isolate a system, you see, we never have 100% isolation. There's no 100% isolation. That basically means that there's a heat flow. There will be whatever system you have, there will be a heat flow. If you make a change that is very, very slow, in that case, well, during the change to take place, there will be heat flow, so it's not an adiabatic process. So the adiabatic process has to be fast, but not too fast, because if you move, let's take this example of a piston. If you move this piston too fast, then it's no longer, it's not even an equilibrium process, because you are creating heat by that during that non-equilibrium process. So a diabatic process, yes, is no exchange of energy, but depending on what you are comparing it to, it can be fast or slow. It is fast. It should be fast enough so that there won't be any heat exchange in a realistic system, but it should be slow.
Should it be faster than the relaxation?
Yes, that is the characteristic time of what we call the fast or slow. It should be slower than the relaxation time, in fact. So relaxation time is the time it takes for a given system to reach equilibrium once you disturb your system. For example, if you are pushing this piston down, you see, here I said the mechanical equilibrium and thermal equilibrium. Thermal equilibrium is when you can define a temperature for the whole system. Mechanical equilibrium is when you define a pressure for the whole system. My whole system has a definite pressure. Now, if you push this piston, you will be initially compressing the atoms over here. So you are increasing the pressure in the near vicinity of the piston. But if you do it slowly, slower than the, let's say, if the piston moves much slower than the speed of sound for a gas, then while you are pressing, the pressure will equilibrate. That is the relaxation time. So almost instantaneously, if you push the piston slowly, at every instant, there will be a single pressure defined throughout my gas. This happens as long as the velocity of my piston is much slower than the velocity of sound. That is the velocity with which the pressure wave moves. You don't buy it?
Bicycle pumps get hot. Bicycle pumps get extremely warm, and the
Okay.
velocity is far lower than the velocity of sound.
We will see that later on.
Okay.
You see, compression changes in an adiabatic process, the pressure changes.
Okay.
So that is where in a non-ideal gas, the bicycle pump should get hot. Plus there is the friction also.
I'm confused.
Yeah.
So
Forget that example.
basically,
Okay.
you're saying that when we press the piston down slow enough,
Mhm.
the pressure should equalize itself and return to equilibrium.
At every instant, the pressure will be at equilibrium.
Then how do cars stop? Because when I press the pedal slowly, it still stops.
Okay.
The pressure is transferred to the brakes.
I didn't
So
understand your
there is no-
example.
it could-
I didn't understand your example.
The pressure change of
Yeah.
that piston, of me pushing, translates to braking power.
Yes.
If the pressure was in equilibrium, then it wouldn't change and not stop the car.
This is basically my brake, right?
Yeah.
So there's some pressure over here. There's probably some spring mechanism over here also. The forces are in balance. I push this piston, which translates to an increased pressure. If there is an increased the pressure increases, but I'm not saying that the pressure at this point increases. Pressure everywhere increases. So at every point of this hydraulic liquid, there is an increased pressure. That increased pressure pushes this piston against the spring. And so this brake comes into contact with the wheel and the wheel stops. But at every moment during this process, the pressure in this liquid is the same at every point. That's basically what I'm...
Delta T.
Hmm?
So in delta T time.
During that delta T time, the pressure throughout the fluid is the same. That is what I mean by equilibrium.
No.
No. You see, the idea is if you change the pressure in a gas, in any material, you are basically creating a wave, a sound wave. And it takes some time for that sound wave to travel through. So what we want is, at least if our system is in in mechanical equilibrium, when I say that my system is in mechanical equilibrium, I'm saying that every point in my system has the same pressure. So when I push this piston a significant amount, it should be in a time, the time it takes for me to push the piston a significant amount should be smaller than the time it will take for the sound wave to travel around, bounce back a couple of times. Then my system will come to equilibrium. That will be basically the definition of slow enough, or in other case, fast enough. So you see, for example, here, the relaxation time determines how fast my system comes to equilibrium. So any change we do should be slower than that. Those are the systems that we will study. We will not be dealing with non-equilibrium phenomena. To an extent, what we learn can still be applied to non-equilibrium phenomena. In that case, what will happen is, let's go to this example of heat transfer. I said that this is not an equilibrium phenomenon. But this reservoir itself is in equilibrium. Well, if I take a small slice over here, if I look at this system only, in that very small, thin slice, that slice will still be in thermal equilibrium. I can define a temperature for that slice. Let's say if it's at a distance x, that slice has a temperature T of x. So each one of those slices will be in equilibrium. So whatever we learn here will be applicable. The only thing we need to add is how these systems that are in themselves in equilibrium, how they interact with each other. So that is something we have to add. These are so-called quasi-equilibrium systems. Again, those are not the systems we will study. But although we are looking at only equilibrium systems, they can still be applied to some non-equilibrium systems also. The same concepts, the same ideas. Now, let's start with the laws of thermodynamics. So who knows about the zeroth law?
Really trivial and I always forget it.
Yeah, all the laws of thermodynamics, they seem trivial, but
Yeah.
they have far-reaching consequences.
A and B are in equilibrium and C is the transitive one.
Yeah. Well, what it tells me is that if A and B are in equilibrium, with C, then A and B are in equilibrium with each other. Well, this law basically allows me to claim that there is a quantity called temperature. Well, for those who are more inclined in mathematics, basically this defines an equivalence class. So let's say that I have many systems. Lots of them. And then I determine which systems are in equilibrium with 1. All of these systems are in equilibrium with 1. Then I will have a group of other systems which are in equilibrium with 2. A group of systems which will be in equilibrium with 3, etc. So this basically tells me that for any system, I can just determine with which it is in equilibrium with among these. Then I can call its group. It's just a member of this set or the member of the other set. Well, rather than calling it 1, 2, 3, I can just call them 1 degree Celsius, 2 degrees Celsius, or 274 degrees Kelvin, 274 Kelvin, 275 Kelvin. It's just the naming. So the idea is there exists such a quantity. This law tells me that there exists a quantity, a single one, which will allow me to determine whether two systems are in equilibrium with each other or not. This is what this law tells me. Now, of course, we will define what the temperature is, what the Celsius scale or the Kelvin scale are. But this law tells me that there is a parameter. Well, in this case, it's just the number of these samples. There is a single parameter which allows me to determine whether two systems are in equilibrium or not, and that parameter is what we call the temperature. So what Zero's law tells me is that there is something called temperature. It exists. Now, so that we have the temperature, we can use it. What is the first law?
Conservation of energy.
So what are these things? Delta U is the change in the energy of the system. Delta W is the work done by the system and delta Q is the heat given to the system. And you can ask, what is heat? Well, heat is anything that changes the internal energy of a given system except the work done by the system. Everything else is what we call heat. Well, this is more than just the conservation of energy, by the way. Let's do some examples. Let's look at a couple of examples. Let's stick with the work done. We had the example of friction. Let's say that we have a surface with friction. I'm moving my block, my mass from point A to point B. Let's say that the friction, their separation is 1 meter. The friction force, let's say, is 1 Newton. Let's say that I just push this block from A to B straight away. What is the work done?
1.
Yeah, it's just 1 Newton times 1 meter. What's the work done by friction, which is 1 joule. It's the work done by friction. So if you want to move it from A to B, you have to do this much work on the object. Well, if you want to be more formally correct, it's -1, the friction force in the opposite direction. Well, let's say that rather than taking it straight to B, you move it first to C, and then from C to B. What is the work done? Again, 1 Newton. In total, you moved 3 meters. So it's minus 3 joules. So you see, you started from the point, in both cases, you started from point A, and you reached the point B, and the work done you did was different. So you just cannot write the work done on this object as the difference of two properties of the system at the point B and the point A.
Non-conservative.
It's non-conservative. So when we say delta W, you see delta, we usually use the symbol to denote change. This is not equal to omega final minus omega initial, because there is no function omega.
Sorry, it doesn't work.
There is no function omega. It doesn't exist. So you cannot write a function omega which depends only on the state of my system. The work done doesn't depend only on the initial and the final states. It also depends on how you went from the initial state to the final state. Similarly, delta Q is not equal to Q final minus Q initial. There doesn't exist functions omega or Q, functions of the state of my system that's called the work or the heat. They just doesn't exist. They don't exist. You cannot define them. But you can do this. There is a state function called U, the energy of the system. The energy of the system depends only on the internal state of the system. It doesn't depend on how you come there. And delta U is nothing but the change in this state function. So if you go back over here to the first law, you see the work done by the system cannot be described by a state function, a function of state. The heat given to the system, again, it cannot be defined as a function of state. But their difference is a function of state. So, which, as we will see in a moment, will have important consequences. You see, most of thermodynamics basically relies on the fact that if you have a function, this is a strong if you have a function, if you take its second derivative, you can change its order. But this you can only do if there exists a function f. Well, where will the derivatives comes into the game over here? Well, derivative is nothing but change in the function divided by the other parameter, the change in the other parameter. But this, we cannot define the derivative of q, because q doesn't exist. We cannot define the derivative of omega, because omega doesn't exist. Okay, that is something to keep in mind. Now, any questions here? Now, let's do an example. Let's do some simple applications of it. The ideal gas. Well, for the ideal gas, we know that PV is equal to NKT. Let's say monatomic. And so for an isothermal process, Isothermal, meaning T is equal to constant. PV is constant. For an adiabatic process, that is Q, there is no heat exchange, delta Q is equal to 0. By the way, heat exchange doesn't necessarily mean that my system is not interacting with another system. There is nothing that creates heat in the system. So, for example, you can have a piston. You can just push the piston very hard, very fast. This is not an adiabatic process. Although it's not interacting, it's not exchanging heat with the environment. The fact that you pushed it very hard, you have created a sound wave, and that sound wave, the energy of the sound wave will eventually be converted into heat. So that is again not an adiabatic process. Although except that you doing mechanical work, you still created heat in the system. You transferred heat to the system. So for an delta Q is equal to 0, and PV to the gamma is constant. For a monatomic ideal gas, gamma is just a constant for 5/3. Okay, we will derive these. And the energy of the ideal gas, 3/2 nKT. Well, I'm just writing down these equations for this example, but we will derive all of them. So let's look at certain processes. Let me look at a PV diagram of, I have a piston, frictionless, is filled with ideal gas. It's isolated. Okay. Now, let's say that, first look at an adiabatic process. There is no heat exchange. I initially start with a large volume, let's say at V2. Let's say I just compress it to a volume V1. I know that since I'm compressing it, the pressure will increase. Well, PV to the gamma will be constant. V is getting smaller. I'm compressing it. So the pressure will increase. Oh, sorry, this is V. This is P. So this is how my system will behave. So the first question is, how much work is done by the system? Well, the work done, let me use a symbol. Well, you will see many notations used. Since there is no function omega, this is not the change in omega or the differential of omega. In some books, they just put a bar on D to denote that it's not the differential of anything. In some other books, you will see this delta omega, small with a small delta, but always keep in mind that this is not the differential of anything or the change in anything. So you can only calculate these quantities for a given process. So that is why I'm specifying my process here first. So I have my system, that is the piston. And I am telling you that I am compressing my system in an adiabatic process. There is no heat exchange with the environment. For this process, I can calculate the work done. If there's another process, the work will be different. Well, the work done, remember, I'm not talking about the work done. I'm pushing the piston. I'm not talking about the work that I did. I'm talking about the work done by the gas. So the work done, the definition of work will be F dot del This is for the force exerted by the gas. Well, in this simple system, the force is vertical, the displacement of the piston is vertical, they are pointing in opposite directions. So this is minus the force exerted by gas on my piston multiplied by, let's say, dx, the displacement. The force, the definition of pressure is nothing but force per area. So force is pressure of my gas times the area of the piston times dx. But this dx is the change in the position of the piston in some small amount of time. So you see, this is my dx. But that product is nothing but the change in the volume of my gas. Let me put a minus sign. Because you see, dx is positive. Dx here is nothing but the length of dl. But dv is negative. Basically because dv is the change in the volume. You see, dw is not the change in omega, but dv is the change in the volume. So this is p times p dv. Well, this is in general will be correct. Whatever system you have, if you change the volume of your system slightly by an amount dv, the work done by the system will be p times dv. So if you like, you can write delta u is equal to delta q minus p delta v. Of course, this is assuming that I can talk about the p during this pressure change, which means that I should change the volume in such a way that at every moment the P should be well defined, and which means that my system should be in mechanical equilibrium. Okay, now let's come back to this example over here. The work done, the total work done in mechanical equilibrium, so that there is a pressure. I can talk.
What's the difference again?
In mechanical equilibrium, I can talk about the pressure. In thermal equilibrium, I can talk about the temperature. Equilibrium is when both of these exist. I have both the pressure and the temperature. So the total work done by the system will be just the integral of p dv. Well, let's see. You see, p v to the gamma at every moment will be equal to p 2 v2 to the gamma. So pressure I can always write as P2 V2 to the gamma divided by V to the gamma dV, while the volume changing from V2 to V1. This is the work done by the system. Yeah, let's just integrate it out. V to the minus gamma plus 1, 1 minus gamma, V changes from V2 to V1. It is P2, V2 to the gamma, divided by 1 minus gamma, 1 over V1 to the 1 minus gamma minus 1, minus 1 over V2 to the gamma minus 1, which is P1 V1 divided by 1 minus gamma minus P2 V2 divided by 1 minus gamma, where I also use that P1 V1 to the gamma is P2 V2 to the gamma. Right. Well, the problem is with the connections that it's flickering. So this is the work done. What is the heat given to the system? You see, in this equation, we have basically three things. We now know delta W. We just integrated PdV during the process. What is delta Q?
We're going to be assuming a diabatic process.
Yeah, so delta Q is 0. The process already tells me what delta Q is, so we now know what delta U is. Which also tells us how much the temperature changes. Because delta U would be just but of course you can basically do the same thing from the adiabatic equation and the equation of motion. You say we know that PV to the gamma is constant. Well, PV to the gamma is PV times V to the gamma minus 1. But PV for an ideal gas is always NKT, V to the gamma minus 1, which is constant. Well, this tells me that T times V to the gamma minus 1 is constant. So you can also calculate how much the temperature changed. Well, basically the idea here is in a given process, depending on the process, well, these are the three things that you somehow need to calculate. This was easy. It was an adiabatic process, so delta Q was 0. For an isothermal process, we can basically do the same thing for an isothermal process. For an isothermal process, temperature is constant, so internal energy is constant. So delta U is 0. So by calculating delta W, we know what delta Q is. So if we want to compress or decompress an ideal gas, keeping its temperature constant, we are forced to extract heat or give heat to the system. Let's give a 5-minute break if you like at this point, and then we will continue.
Hocam gamma numerik olarak bulunmuş bir şey mi yoksa
Well, this gamma, for an ideal gas, you can measure it in the experiments, or we will calculate it.
which one came first?
I don't know.
It looks so much